Control Mode Specific Application or CMSA and Early Suppression Fast Response or ESFR sprinklers are designed to be more effective for high challenge fires and are commonly used to protect storage occupancies. When applied under the right conditions, these sprinklers can also help reduce the overall system demand. In this video, we will become familiar with these types of sprinklers and examine how to determine the design area where they are applied. Control Mode Specific Application or CMSA sprinklers are a type of spray sprinkler capable of producing relatively large water droplets. As the droplet size increases, their mass and ultimately their momentum also increases. This allows the droplets to penetrate more effectively through the fire plume, reach the fire source, and help control the fire. CMSA sprinklers can be either upright or pendant and may be used in wet, dry, or pre-action systems. The maximum coverage area and spacing for CMSA sprinklers depend on several factors, including the combustibility and obstruction characteristics of the building construction, as well as the type of storage being protected. One interesting requirement is that the standard specifies a minimum coverage area of 80 square feet for CMSA sprinklers. This requirement helps prevent a phenomenon known as skipping. Skipping occurs when sprinklers do not operate in their normal pattern, causing sprinklers located farther from the fire to operate before those closest to the fire. In the 2025 edition of NFPA 13, the installation rules for CMSA sprinklers have changed significantly and now explicitly parallel those for ESFR installations. This is one of the most useful updates in the 2025 edition, since the installation requirements for CMSA sprinklers in earlier editions were quite complicated and, in some cases, did not align well with other provisions of the standard. For example, the beam rule exception in the 2022 edition simply stated that sprinklers could be installed on the opposite side of the obstruction, but it did not specify the required distance between the sprinkler and the center line of the obstruction. In some cases, this could leave a portion of the floor area unprotected and increase the potential for fire development. In the 2025 edition, because the installation rules now follow those for ESFR sprinklers, the beam rule exception specifies that the distance between the sprinklers and the center line of the obstruction must not be greater than half of the sprinkler's maximum allowable spacing. This helps ensure that the floor area is fully covered. Regarding hydraulic calculations, Chapter 22 provides 6 tables and Chapter 24 provides 3 tables covering different commodities and storage arrangements. In these tables, based on factors such as the storage arrangement, commodity class, maximum storage height, maximum ceiling height, and the system type, the standard specifies the applicable K factor, sprinkler orientation, number of design sprinklers, and the minimum operating pressure. In some cases, the tables provide multiple options for a specific hazard, and designers are allowed to select any of the listed options. For example, if we want to protect cartoned, non-expanded Group A plastics stored on pallets with a storage height of 20 feet and a ceiling height of 30 feet using a wet pipe sprinkler system, the table provides 4 options based on the sprinkler K factor. If a K factor of 11.2 is selected, the design area includes 25 sprinklers with a minimum required pressure of 25 pounds per square inch. If K factors of 16.8, 19.6, or 25.2 are selected, the design area includes 15 sprinklers, with the minimum required pressure varying based on the selected K factor as specified in the table. The designer can select any of these options based on the project specifications. For example, if the available water supply pressure is relatively high, choosing a lower K factor can help reduce costs by allowing the use of smaller sprinklers. On the other hand, if the available water pressure is limited, selecting a larger K factor may help achieve the required flow without the need for a fire pump. After determining the number of sprinklers in the design area based on the tables, the next step is to understand how to select these sprinklers in the project layout. To do this, we follow section 28.243. The procedure for determining the design area is similar to that used for standard spray sprinklers. However, instead of selecting a value from table 19.2311, the design area is calculated by multiplying the number of sprinklers specified in the CMSA tables by the actual floor area covered by those sprinklers. The rest of the procedure is the same as for standard spray sprinklers, which we explained in the previous videos. Let's review these requirements with an example. Imagine the storage configuration described in the previous example, where the sprinklers are spaced 10 feet by 10 feet and 𝐑𝐞16.8 sprinklers are selected. According to the table, the number of design sprinklers is 15. First, we calculate the coverage area of each sprinkler. With a spacing of 10 feet by 10 feet, each sprinkler covers 100 square feet. Multiplying this by 15 results in a design area of 1,500 square feet. Next, using the formula, we calculate the length of the design area, which equals 46.47 feet. Based on this length and the sprinkler spacing, we determine that there are 5 sprinklers along the branch line. Therefore, from the second and third most remote branch lines, we select 5 sprinklers on each line to reach the total of 15 sprinklers required by the table. For the hydraulic calculation, we assign the minimum pressure required by the table for the 𝐾16.8 sprinkler, which is 22 pounds per square inch at the most remote sprinkler. Then we calculate the corresponding flow rate and continue the calculation following the same process we reviewed in the previous videos. As a final note regarding CMSA sprinklers in this video, remember that in Table 22.2, the requirements specified for dry pipe systems may also be applied to pre-action systems. Unlike typical sprinklers that are designed primarily for fire control, ESFR or early suppression fast response sprinklers are specifically engineered for fire suppression. To understand why this is such a massive advantage, let's review the standard fire curve. This will help us clearly define the difference between fire protection terms like fire control, fire suppression, and fire extinguishment. First, it is important to look at how a fire behaves naturally without sprinklers. Engineers plot time against the heat release rate, or HRR, which represents the amount of heat energy the fire produces. An uncontrolled fire goes through 4 clear stages. It starts with ignition as a small, localized flame. It quickly moves into the growth phase, where the HRR increases rapidly, often proportional to time squared. It then reaches the fully developed stage, leveling off at its maximum heat output. Finally, as it runs out of fuel or oxygen, the fire enters the decay phase, and the HRR steadily drops. As we know from mathematics, the integral of this curve, which is the total area under the curve, equals the total heat released during the fire. Ultimately, the larger this area is, the more severe the damage to the building. Now, let's see how our 3 fire protection terms change this curve. The first concept is fire control, which is the main goal of traditional sprinkler systems. When a sprinkler activates during the growth phase, it effectively caps the curve. It limits the heat release rate and stops the fire from spreading, but the fire continues to burn at a steady rate. The system simply keeps the fire contained until firefighters arrive or the fire runs out of fuel or oxygen. The second concept is fire suppression, which is the major advantage of ESFR sprinklers. Instead of just holding the fire back, an ESFR system is designed to actively attack it. It releases large, fast-moving water droplets that penetrate the fire plume, forcing the HRR curve to drop sharply. It goes beyond basic control by actively reducing the fire's power. Finally, we have fire extinguishment. This means the fire is completely out and the HRR drops to exactly 0. Gaseous systems are a great example of systems specifically designed to achieve fire extinguishment. When it comes to water sprinklers, If we are lucky, the system might also extinguish the fire completely. However, depending on the type of sprinkler installed, we technically only expect them to either control or suppress the fire. The second interesting topic regarding ESFR sprinklers is the term fast response, which is directly related to the sprinkler's response time index, or RTI. In NFPA 13, we frequently encounter two very similar terms, fast response and quick response. But what exactly is the difference between them, especially since both require an RTI of 90 square root of foot-seconds or less? The easiest way to understand the distinction is that fast response is a broad category, while quick response is a specific listing. Fast response is an umbrella term. It refers to any sprinkler with a thermal element designed for superior heat sensitivity compared to standard response sprinklers. Because of their highly sensitive thermal elements, ESFR, residential and quick response sprinklers all fall into this broad fast response family. However, when we say quick response, we are specifically referring to spray sprinklers. In simpler terms, when a fast response element is used in a spray sprinkler, it becomes a quick response sprinkler. The difference between fast response and quick response was one of the questions in the Top Tech competition held by the National Fire Sprinkler Association in 2007. Regarding coverage area and spacing, Table 142721 specifies a maximum protection area of 100 square feet. The table also outlines the maximum allowable spacing based on ceiling height. For ceiling heights up to 30 feet, the maximum spacing is 12 feet, and for ceilings above 30 feet, the maximum spacing is reduced to 10 feet. To prevent skipping, the standard defines a minimum coverage area of 64 square feet for ESFR sprinklers. Regarding hydraulic calculations, Chapter 23 outlines the requirements in Tables 23.3.1, 23.5, and 23.6, as well as Section 23.4. These tables are similar to those for CMSA sprinklers, with one key difference. Tables 23.3.1 and 23.6 do not specify the number of design sprinklers. Section 23.2.2 provides the general rule, stating that the design area shall consist of the most hydraulically demanding 12 sprinklers, with 4 sprinklers on each of the 3 most remote branch lines. However, NFPA 13 also includes exceptions to this rule. For example, for certain piling methods used in rubber tire storage, the required design area increases to 20 sprinklers, arranged as 5 sprinklers on each of 4 branch lines. Another example appears in Section 28.2.441, where the design area increases to 18 sprinklers when required due to ceiling slope. In that case, the design area consists of 5 sprinklers on each of the 3 most demanding branch lines plus the 3 most demanding sprinklers on the next most remote branch line. As you've seen, we reviewed the basic concepts related to CMSA and ESFR sprinklers. In the Storage Warehouse series, we will cover the remaining requirements in greater detail.